basically, you have, if you've understood it, you've understood what Gaia is about. So that is like you have this page, you have the points, and you're trying to find the best way to deal with similarity. There's one quick feature I'm not going to show you because it's going to take some time. Then you can also filter some points. So when you say, okay, give me all the nearest neighbors to this one, you can say, but only the ones that have a value of ppm which is higher than 120, or the ones that have a key as being though major or minor. Same, like basically, same as you can do it in a SQL database. What we're going to do now is I'm going to do a little bit more complex example, but the concepts are all going to be the same. That is, I'm going to take my input data set, going to take the information I want out of it, because I will not use all the information that's in there, and make a distance that's a bit more complex than just a Euclidean distance. I'm going to try to make like a smarter distance, or more complex one. So I'll start from scratch. I'll go faster on what we've already done, and then I'll go slower when it starts to be complex. So the first thing is I get my data set. I load my database, which is called now, what would I want to do? So I'm going to do a PCA of all the mean descriptors that I have in my dataset, because I think that the mean is enough, like I don't care about the variance. And I'm also going to use, very quickly, Kullback Leibler. So this is a distance. When you do the mean and the variance, you actually discard lots of information, because you're reducing like all your frames to a single value. You're aggregating all of it. Sometimes, for instance, let's say I only want to use the mean of some descriptors. If all of them are 0, the mean is going to be 0. If half of them are -1 and half of them are 1, the mean is going to be 0. So you can see those two are very different cases, but the mean, because like I'm losing information somehow, I might lose important information. You hope not, but you never know what might happen. So the Kullback Leibler distance is a distance that does work on the correlation matrix. So instead of just taking the mean or just the variance of all your frames, you take the covariance matrix, where it's a lot more information. So if you have, let's say MFCC, you have 13 descriptors, you have 13 coefficients in the MFCC. If you take the mean, that's going to be 13 values. If you take the variance, that's going to be 13 values. If you take the covariance matrix of all the frames, it's going to be 13 by 13, so that's 169 values. It's about, well, it's not about, it's exactly 13 times more, but you get lots of information that it's still compressed, because in a song you might have thousands and thousands of frames. You compress this to a 13 by 13 matrix, so it's pretty good. And coupled with the Kullback Leibler matrix, you're going to see it in lots of in the literature, because it's very useful and it achieves very good results, much better than what you would only get with the mean and variance. So it's kind of a trade-off. I'm saying that for the MFCC, if you look at all the descriptors I have here, most of them I have only mean and variance, because I assume that they are like limited usefulness to me, or I don't know which usefulness. The MFCC, which we know are quite useful, you see that we have the mean of the MFCC, so that's like those 13 coefficients I'm talking about. plus the covariance matrix. So as you see, there's like 13. That's the first line, that's the second line, second row, third row. That's what you have for the MFCC. It's a lot more for the as for the others, but it's also much more useful. So the idea is that with my dataset, I'm going to take the PCA of all the mean descriptors on one side. I'm going to take the covariance matrix and the pullback Leibler on the MFCC on the other side. And I'm going to create a distance, which is a mix between those two. For instance, because you say that the MFCC, you want to have like information that's very relevant to the spectral shape, melodic aspect, and the other ones, you want to convey some other aspect. In a more high-level example, you could say that you have a distance which is like very based on tonal features, and another one on rhythm features. And then, for instance, depending on the user, you could change your distance depending on what you want to do. If you want to have something which is more rhythm-focused, just get the rhythm distance as well. So, the first thing is I'm going to prepare my data set. So, on the one hand, I want the PCA. So the first thing I have to do is, don't forget, I'm going to normalize it. So I transform my data set, normalize. I don't give parameters, I just want to normalize all the descriptors. That's fine enough for me. Yeah, actually, I should have personalized it, so let's do it now. So I said before here, I could do it on the normalized or the normal one, that's fine. And then I do the PCA. So this is just the one taking all the data I have at the beginning and making a subset which is useful for me. Gaussian data set. You want the PCA. The PCA, you're going to have to give arguments to it. If I look at the documentation, so you have the usual descriptor names and except to choose on which descriptor you want to compute it. Given that the PCA is going to take all those descriptors and mash them into a single one, you have to give the name of the resulting descriptor. And you need to give the dimension. As said before, it's used a lot for dimensionality reduction to go like from 400 descriptors to 20. And it can actually go down to whichever dimension you want. You can either specify the dimension, you say I want 20 dimensions at the end, or the variance, like the variance in your data set that should be covered. So you can say, I don't care the variant, I don't care about the dimension, but I want to make sure that I include 90% of the variance when you do this machine. I'm going to go with the dimension because it's easier. So here, if I create the PCA like that, it's going to complain. I say I cannot because you need to specify the dimension. So in particular, this is the same way as you specify the parameters for the distances. It's a dictionary of parameters. So you say the dimension should be 20, and you also need to give the result name. The result name should be like 8.2. So what this did, it took all the descriptors in my dataset and it did the PCA transformation, and as a result, as the result of the transformation, before you could say, okay, one dimension is the MFCC, one dimension is the BPM, and one dimension is this thing. Given that you rotate the whole thing, this doesn't make any sense anymore because each dimension is going to be a mix of lots of others. So the names disappear, so you only get one single big descriptor. Which means that before doing the PCA, for instance, your dataset layout was like this. So basically you have all the same descriptors as the beginning because I only normalized. So if I normalize, if I Gaussianize, I'm not changing which descriptors are in there. I'm only changing the values. After doing the PCA, it looks like this. I only have a single descriptor in my dataset, which has 20 dimensions, which is why I asked for. Yes. So this is like a compressed version of my original dataset. The problem is, if I want to compute the distance, which is a mix between this and the other data that was in the original dataset, I need to get them in the same dataset. I cannot do it separately. So what I will do is like my dataset with everything. You have this function which is merge dataset, which basically, if you have two datasets, one like that and one like that, it's just going to create one big one, which contains all the data from both datasets. To be able to do this, you have one obvious condition: is they need to have all the same points. Like they need to have all the same points. So to merge them, I just merge my original dataset and the dataset that contains the PCA. Okay. And now if I look at the dataset all, like the layout of this dataset, what it contains all those descriptors that were in the original dataset, and it also contains this descriptor here, which is the PCA that contained everything. I've joined them together. So now I will be able to do a distance on this dataset using both the PCA and the original values. As said, there's also ways to import different values in there from the outside. For instance, if you have a different source of values, you could create a new descriptor and put it there. So I want two distances. The first one, I'm going to go with the Euclidean distance. So I could create it like Euclidean distance and everything, but to do the linear combination, it's a bit tricky. That's the reason. So again, skip this thing at the beginning. What you want to have as parameters is you want to give a parameter map which contains the list of distances you want to mix together, you want to blend together. And each of those should contain those three fields. The name of the distance you want to use, the parameters for this distance, and the weight for this distance. So in my case, let's say that I want to use like 0.4 times the Euclidean distance and 0.6 times the other distance, the Kullback-Leibler. So instead of creating them separately, because if I create them separately, then there's no way to merge them because they're already created. So I need to specify the parameters like that. So the parameters for my Euclidean distance are the following. Distance is the Euclidean distance. The parameters are, I don't want to compute the Euclidean distance on all of them. I want to compute it on the PCA descriptor. It's called descriptor names, not descriptor name, because you can specify a list. In this case, I have only one, but the parameter name is still the same. And the weight I want to give it is like 0. Okay. Now for the callback library distance, this one, you see that I need to give only one parameter, which is the descriptor name. So in this case, the MFCC, the documentation tells you that you need to have the mean, the covariance, and the inverse covariance. That's a good thing because it's already in there, because Essentia computed like the three of them. There's inverse covariance, the covariance, and the mean. So basically, what I'm going to tell to the callback library distance is that as a distance, I want a callback library 1 as parameters. I'm telling that the descriptor name is MFCC. And as a weight, I'm going to give it 0.6. And now I can create my linear combination. Yes?
Inside params,
yes.
What is the param? Descriptor name, so descriptor name, or are both different?
They are different. Most of the time it's going to be descriptor names because you can compute the distance on multiple descriptors. So for instance, Euclidean distance, you could say, I want the Euclidean distance of this, and this descriptor. So the parameter is called descriptor names, and you can give the list. Actually, to be, I mean, this works too, but what it is this actually. It's a list. If you want to specify more descriptor here, you could specify more descriptor. For the callback library, you cannot give a list of descriptors. I mean, you could, but it's more complex. But because it needs like one descriptor and the mean and the covariance and the inverse covariance, so it's kind of more specific on, let's say, more focused on a single descriptor. So in this case, for the callback library, the parameter name is single. If you see the documentation, it's good. But actually, the callback library is the only one. No, it's one of only two that has this descriptor and singular. All the other distances that I can think of at the moment have it plural. Because you can always specify, like, depending on the distance, you could always specify like a feature vector on which it should apply. Except for very specific ones which work like only on one descriptor. All the ones that accept descriptor names also accept except. Like you want to remove, for instance, you say, give me all the spectral descriptors. So you say descriptor names, spectral star asterisk, except the spectral centroid. So it would accept and spectral centroid. Okay. So these are my parameters, and then for the linear combination. So it says you just have to give a map of name. So here the name is not really important, so that's my hidden params. And you give them the parameters. So that's one part of the distance of my linear combination. And this one is the other part. Conceptually, this is just it's very simple. In practice here, it's a bit complex because of the syntax. So that's the reason we're doing this together. you should be able to do everything with the documentation, more or less, except this one, which is useful very often and is not so obvious to write correctly the first time. So my distance, well actually, so I want to create it, and remember that you always remember on which data set you work. It's important. So if I create this linear combination distance, I want to create it on the data set I had at the end, which contains all the descriptors. You don't want to create it on the first data set because you're not going to be able to. The first data set doesn't have the PCA descriptor. I have my distance, I have my view, well I create my view on this data set, and now I can do queries again. So I need a point. So that's the first point of my data set. That's the distance, and if I want to see 10 closest results, it's going to give me this. So, two things. First, you see that after normalizing, doing Gaussianize, everything, the distances have better range. I mean, you see more stuff. It's a bit coincidental, but not entirely. The other thing you see, for instance, here, you have this one, which was my query point. So it always comes out first. If I would load a point from SNCR from outside the dataset, you would have distances which are not zero. Here, you get the zero because this point is in the dataset. So if you're looking for this point, here, I take it from the dataset, but I can take it from outside. I take it from the dataset, so it's already in the dataset, comes out first, distance zero, because you're looking for this point. Here you see that I have one which has a very similar name, but more than that has a very low distance. Like you see, the first result is like 0.02. The next result is 7.7. This happens because in the database, this database, there are some files which are they're not exactly copies. I don't know what has been applied to them, but they're duplicates, which means they're the same song. You're going to listen to it, they're going to be the same, but they're not the exact same file, so the distance is not exactly zero. Here, well actually here you can also see that this one and this one, they're about at the same distance as here, because they're duplicates. So now, if we want to do more advanced stuff, I mean, like, this is all there is to it. I mean, like, we could go on doing more complex distances and everything, but I think I'm boring enough as it is. You probably, if you want to do this, or you want to use it for your thesis, you're going to take it with more time and go like step by step, like trying first simple distance and then like building more complex distances. There are some quite complex distances that we can do using lots of higher level descriptors, because this here I've been working on Euclidean distance on spectral descriptors, which is very low level. I mean, like it's just like basically values and just Euclidean distance. Dimitri Bogdanov, for instance, is working on it and using SVM classification probabilities for songs, of the fact that the song is like 60% rock and this, and then using distances on top of that, which have been shown to be quite useful and powerful. But you get to them after, I would say, after a lot more practice. The thing that's interesting to go there is like making useful application of this, because the concept's very simple. You just get the closest points. For instance, I told you before I could do genre classification. So if you look at this folder, where I have the file, we'll go very quickly on it. They are classified in folders which are the genre. Okay. So you could say, well, okay. Well, let's say I find another point which is not the case, like this one. So if I search for this point, if I don't know the class of this point, I could just say it's the class of the next point. So here, very quickly, you don't have to follow me here. Yes. So, yes, I don't have the folder, so I'm going to create them very quickly. I'm going to say that in Python there is a module called OS, does lots of stuff. In particular, a function OSWalk, which recurses into a tree of directories. So if you see this, just look at it, not try necessarily. So I say from this folder where I'm in, this is the one I'm in. So it tells me the folder where it goes into and the files that are in there. If you look at the database, the names of the points are the file names without the .sig. So here I'm just creating a ground truth really quickly. You don't need to understand what I'm doing, just know that what I'm going to do is for each of those points, okay, each of those names, I'm going to put the genre in it. So I go in all those files. What I'm going to do is that for each of the files, the ground truth of the file minus the 4 letters, is minus the extension. If I take the file name, I remove the 4 last letters, and I say that the ground truth for this is the root folder minus the 2 first letters. Just so that you know, this is what I have in my ground truth now. So I have all the file names, and they are associated, that's not the genre, they are associated genre. So this very quickly. So if I go back to my distances, Gaia, actually let's say, so where I'm getting a point here. Let's say if I want the genre of this, I need to get the closest neighbor. Okay, so I do this, I use my distance. I get, actually as this one is in it, I need to get the second one. So I can only get 2 results and I get the second one. Okay. Actually, let me do it in multiple steps. So neighbors is this. So the closest point to this one, which is not this one, is this one. So it's second element, and I want the name, I don't care about the distance. Sorry. Okay. And then I can look the ground truth of this file. So for instance, given that I have all this distance, which is working very well, and that my similarity is working very well, I can do very quickly a function which will, to get the genre of a point, what it's going to do, it's just going to look for this point using my super distance. It's going to get the result, and actually it's going to return the ground truth of the closest point. This is just to show you that it's one-liner. It's not very comprehensible, but then you can do stuff like I want to guess the genre of this point. Well, actually,
But it's a function.
yes, it's a function that does all the squares at once. So boogie woogie stomp. If I look for this. It's in blues, okay, and it worked, yeah. Because when you look for the similar to this song, and because we, actually the distance that I showed you before looks complex, but it's also one that I know works quite well for music similarity. So it was not completely just to make things complex. The closest song to this one, which is in the blues folder, is also a song. I don't know which one, but which is also in the blues folder. So it's just like you want to do genre classification, you don't want to do SVM or this kind of stuff. You could just say, I don't know nothing about how you do genre classification because I don't have a descriptor that says it's rock if there's like 2 guitars, a bass, and a drums. You could say, well, just get the closest one, and there's a very high likelihood that if they're similar and the similarity distance that you chose is a smart one, or one which is like suited to the task. You can do this kind of stuff very easily. And I think I'm going to stop here actually. I need to go further. Quick note about the assignment. The assignment is going to be the same thing. It's going to be uploaded. For the assignment, I'm asking you to do a different task, is to, using the same logic, to do something that detects the duplicate in the database. Like in the database that you can download, there are a few files which are duplicate because they have a distance between them which is not zero, which is nearly zero. So the task is to find them. So like for each of the points in the data set, you look if this point has a duplicate, and if yes, you print it, and if no, and the way to do this is the same thing here, you get in distance, so the assignment just get a simple one, like Euclid in distance, you don't need to make anything complex. If you want to do something complex, you're welcome. But in this case, it's not going to be useful a lot, because what you're looking is, you don't care that your distance is good as long as it's able to say whether it's exactly the same thing or nearly exactly or completely different. If you do genre classification, this is where smart distance works much better, because here you get all the nuances of the values you use. And I think that's it. Any questions about any of this?
You can upload this to the site.
The history.
Cool. Can you load it?
Oh, yes.
This
Yes,
thing,
please.
yeah. Maybe, yeah, okay. Try to upload maybe a clean version or something. I know that this Gaia looks a little bit less funky than Essentia. I mean, at least looks more abstract. It is more abstract. The concepts are a bit harder to grasp, but once you get it, after that, it's just a matter of like fine tuning, looking which descriptors are useful, and finding which descriptors. Was okay. Boring.
About what you said before, using SVM, what is sorry, the difference between the set of the clusters?
No, SVM, okay, so a quick parenthesis. SVM is not in the distance part, it's in the transformation part.